So, this is the second lecture of module 1 on intelligent control. Outline of this lecture would be like this: revision of previous lecture, multi-layered feed forward network, backpropagation learning algorithm, learning XOR map. So, these are the topics we will be discussing today. These are the summary that we discussed in the last class. So, what you are seeing is a single neuron. We have multiple inputs here multiplied with the weight associated with this connection and they are summed up in the summing junction, and then you have an activation function. Okay. And in linear neural network, what we consider, this is simply a constant. Okay. This is simply, I can say this is linear. The batch update law that we said is that new weight vector is old weight vector plus eta into summation of all error terms due to all the patterns, whereas the instantaneous update is done simply the back propagation term due to single input pattern, okay, where delta is the error back propagated. We take another example today, and this example is where we have two poles in the unity circle, within the unity circle, but they are all real poles, minus 0.9 and 0.8, and this is my system dynamics. And so, my model is, this is ypk is w1 yk minus 1 w2 yk minus, this is yk minus 2 w3 uk minus 2, and if I I take a same single neuron with 3 input yk minus 1, yk minus 2 and uk minus 2. When I do that, I finally get these exact values of w1 is 1.7, w1 converges to 1.7, w2 converges to minus 0.72 and w3 converges to 0.02. So, this is what is error is minimum at w1 1.72, minus 0.72 is w2 and w3 is 0.02. So, this the error surface looks like this, and finally, here is the your global minimum. We talked about single layer linear feed forward networks. Now, let us talk about single layer nonlinear feed forward networks. So, in this the activation function becomes nonlinear. So, f is a nonlinear function. The question arises, what kind of nonlinear function we can consider as activation function. So, here is a nonlinear activation function. This axis is x, this is f x, and the function is f x equal to 1 upon 1 plus e to the power minus alpha x. So, by changing alpha value, we can change the transition from 0 saturation to saturation 1. The function varies from 0 to 1, and alpha determines either the sharp rise or very slow rise from 0 saturation level to 1 saturation level. This is a nonlinear function. Why did we select this activation function? If you look at, you may ask, what is the speciality of this activation function? It is very clear in the previous graph of this function that f x is always limited or is limited by the boundary 0 and 1, f x is less than 1, greater than 0. But the interesting part of this function, if I differentiate this function f x, that is f dash x d f x upon d x, alpha f x 1 minus f x. So, you can say that the derivative of such an activation function has a very simple form. So, we had a activation function of this form 1 upon 1 plus e to the power minus alpha x x, and I said that the differentiation of this activation function is very simple to compute. So, if you do that, you see that I get 1 upon square of this and then you differentiate this. So, finally, this is alpha e to the power minus alpha x 1 plus e to the power minus alpha x into 1 upon 1 plus minus alpha x. So, you can verify this function is f x, this function is alpha into 1 minus f x. So, obviously, this one becomes f dash x becomes f x 1 minus f x and 1 alpha here. So, although it is a nonlinear function, its computation is very simple because it is in terms of f x. That is the speciality of this activation function. So, we derived for f x equal to 1 upon 1 plus e to the power minus alpha x, which we normally we call it as a sigmoid function. For this sigmoid function, we showed that f dash x is alpha f x into 1 minus f x. Because of this simple computation, this is one of the reason also for making a choice of this activation function. Now, here is another example of an activation function. The previous one was unipolar because the activation function it has a value from 0 to 1 as you vary the input x from minus infinity to plus infinity. But now, this activation function, when you vary x from minus infinity to plus infinity, you have value minus 1 to 1, minus 1 to 1, and this is a tangent hyperbolic function, and you know that tangent hyperbolic function e to the power alpha x minus e to the power minus alpha x upon e to the power alpha x plus e to the power minus alpha x. Again, alpha is there just to control the nonlinearity in the function. So, the function activation function has a limit from minus 1 to 1. So, we say bipolar activation function, and as we derived earlier, you can derive and you can verify that the differentiation or derivative of this function activation function f x with respect to x is alpha into 1 plus f x into 1 minus f x. Again, it is a very simple computational form. So, for this if we use the sigmoid activation function, that is the previous one, that is 1 upon 1 plus e to the power minus alpha x, then we can go back to our basic principle of gradient descent rule, and if we apply the gradient descent rule for this nonlinear single layer feed forward network, and if you apply the gradient descent rule, you will get batch update. This one is batch update and this is instantaneous update, where the delta is yp 1 minus yp ydp minus yp. Again, as I said, these are all specific to a specific pattern. P refers to a specific pattern. The structure of the update law remains same. What we had earlier, we have the same structure, only difference is that the back error propagated delta has become different. So, I go back now to make little comparison between linear neural network and nonlinear neural network in terms of the similarity and differences. So, I have linear neural network one side here, here nonlinear network. So, in a linear network I have input x 1, x 2, x n, and then you have the computational unit, linear computational unit w 1, w 2, w n and your y. So, in case of linear this is y equal to sigma w I x I. In case of nonlinear the same thing is a nonlinear activation function. So, y becomes f of, it is same as 1 upon 1 plus e to the power minus sigma w I x I. This is a nonlinear network. So, what do we do? We apply the gradient descent rule w I t plus 1 equal to w I t minus eta del E by del w I. So, this is the gradient descent rule. This is applicable for both linear neural network as a nonlinear neural network. So, we have already shown for linear neural network this becomes plus eta delta x I, where delta is the error propagated y desired minus y. So, we are only considering instantaneous update because mostly in control system we will deal with real time implementation, and real time implementation means instantaneous update, we cannot do batch update. So, that is why we will henceforward only consider the instantaneous update, and for this delta equal to y d minus y when it is linear, and you can compute the same thing here for nonlinear network, and you get delta is y 1 minus y y d minus y. So, here we saw that the delta for linear neural network is y d minus y, and we computed the same delta for nonlinear network, and then y 1 minus y y d minus y. So, this is the extra term that comes because of differentiation of f. So, you can now appreciate why f has been selected as sigmoid activation function. This is one of the advantages of computation. And so, now let me take you to the total process of update of weights in simple neural network, linear and nonlinear. So, here it is your input, take a input pattern, allow that pattern to be processed by the network, network actuates y. For each output, each input pattern there is a given y d desired output, compute delta, this delta is y d minus y for linear network, and for nonlinear network it is y 1 minus y y d minus y. So, that error has been transformed. Then you look at here in this side, this is your back error propagated delta, this is your input pattern. Each weight if you look at simply being updated based on its input x 1 and what is the error being back propagated. So, you can look at here the update algorithm is w I t plus eta delta x I. So, for everything you can easily check a very simple rule, the weight update is the original weight plus eta the learning rate into the input and the back error propagated. Although a single layer linear feed forward network can learn any linear map, The same is not true with a single layer nonlinear feed forward network. We took last class and today's class we showed that any linear dynamical system can be mapped or can be learnt using or can be identified using a single layer linear neural network, but this is not the case with nonlinear dynamical function. We cannot identify or we cannot approximate any nonlinear function using a single layer neural network. So, that is the bad part, bad news. But it turns out that a single layer nonlinear feed forward network can only classify those functions which are linearly separable. Okay. So, we showed that the difference between weight update in case of linear neural network and nonlinear neural network when there are only single layer simple neural networks. We also showed that any single layer linear neural network can approximate any linear dynamical system. If we could have mapped any nonlinear dynamical system using a simple nonlinear neural network, probably we would have been happy, but this is not the case. It turns out that a single layer nonlinear neural network, feed forward network, can only map those nonlinear functions that are linearly separable. Those functions which are not linearly separable, they cannot be mapped or cannot be learnt using a single layer nonlinear feed forward network. This is the bad news. So, what is this linear separability? Now, let us consider a simple static function. All of you know an OR function. So, OR network, any OR gate has two input x1 and x2, output is yd. So, these are the truth table. If input is -1, output is -1, and all other cases the output is 1, that is a OR network. Okay. So, linearly separable, we want to address this one. So, we have a OR function, all of you are already aware of the OR function. The truth table is if -1, this becomes -1, and all other cases this is +1. So, this is your truth table. So, given specific input pattern, output is either -1 or +1. Now, let us look at a graphical map of this function. So, -1 is here, this is say 1, this is 1, -1, -1. So, obviously, this is your point where it is -1, and all other cases like -1, +1 you have, and 1 -1 -1 +1 you have plus, and +1 you have a plus. So, you say that if I draw a line here, as a linear line is able to separate a specific class from another class. For this class of input pattern, the output is 1, and for this class of input pattern, the output is minus 1. And this particular function, which is OR function, is known as linearly separable function. Okay? And this can be easily mapped using a nonlinear single layer neural network, very simple. So, to conclude, a linearly separable function, a function is linearly separable if there exists a hyperplane that distinguishes between one class from another class, thus linearly separable. But there are many cases, many functions which are not linearly separable. A very simple example is XOR function. So, let us look at another example, XOR map. In this function, we have input, 2 inputs and 1 output, and the truth table looks like this. So, this is your XOR map. For this case, you have plus 1 output, and the other two cases you have minus 1 output. Let us look at the graphical map. So, when you have minus 1, this is your x 1, this is your x 2. So, minus 1 and minus 1, you have minus, and when you have plus 1 and plus 1, you have again minus, and other two cases you have here plus, that is plus 1 minus 1, and when you are minus 1 again plus 1, you have also plus. So, in this case you cannot find a single line that will separate this class from this class. So, this class cannot be separated from this class using a single line. There is a function where the function is not linearly separable, but this is non-linearly separable. So, I can create a nonlinear decision boundary that separates this class from these two class, this class. The minus class is separated from plus class using a nonlinear boundary, decision boundary. So, this is called the functions which are not linearly separable. So, let us summarize what we discussed now. Limitations of single layer nonlinear feed forward network. A single layer nonlinear feed forward network cannot even approximate an XOR function, that is, it can only approximate those functions which are linearly separable, and there are many complex functions they are not linearly separable. You can refer to Minsky and Pappert's book called for Subtron for more, to know more about this linear separability and nonlinear separability. This book is published by Cambridge MIT Press 1969. However, later the researchers found that if we increase the complexity of the network in terms of number of layers, that we only consider a single layer network, now 2 layer, 3 layer, 4 layer, that is multi-layer network, then such a feed forward network can always approximate any nonlinear function. One of the very key research contributions are by Hornick, Stiscombe and White published in 1989 in neural networks, multi-layered feed-forward networks are universal approximators. So, the problem that we faced from single layer neural network for nonlinear approximation can be mitigated or eliminated by increasing the layers to more than one. It turns out that even a 2-layer network with one hidden layer consisting of infinite neurons can also approximate any nonlinear function. So, when this neural network becomes complex, can we write the learning algorithm very easily the way we wrote for single layer network? So, yes, the answer is yes, little adjustment has to be done, but implementation wise it is not so difficult. The algorithm that was derived using gradient descent for nonlinear neural network with nonlinear activation function is popularly known as backpropagation learning algorithm. Although the learning algorithm still is derived using gradient descent rule. We will make this point very clear why this learning algorithm is known as backpropagation. We gave some hint in the single layer network that error that is computed at output is back propagated, and based on that the weights are being updated, and based on that information the weight update formula is takes a very simple shape, simple structure. Again, when will for a multi-layer network, is it very difficult to derive the learning algorithm? We will derive today. We will show that it is for, we will derive the learning algorithm for 2-layer network today, and in the next class we will show for any number of layered, any the hidden layers may be of any numbers, it can be n capital N, but the learning algorithm derivation is very simple. But all this learning algorithm that we will derive in this course will be instantaneous update rule. Reason being, again as I said, control systems are all real, they require real time implementation, and we have to be considerate from that point of view. So, let us summarize what we are now going to do. This is the focus of this today's class. Multi-layered feed-forward network. It has more hidden layers, and again when I say feed-forward network, the connections are all allowed only from any layer to its succeeding layer, but connections are not allowed from any layer to its preceding layer. The example is, so you see here there are 4 layers, these are all input, first hidden layer, second hidden layer, third hidden layer, and this is output layer. When we say number of layers, we do not count the input layer as a one of the layers. So, when I say 2-layer network, then I have only one hidden layer and next layer becomes output layer, and this particular configuration, that means there are sub units of neurons here, and in this particular configuration if I connect, you will see that the why I say feed forward network, because I am able to connect any layer from its preceding layer. That means, connections are allowed from the preceding layer to any layer, but I cannot allow the feedback connection. This is called feedback connection, is not allowed. This is allowed. From this layer I can connect to this layer, this is allowed, but from this layer I cannot allow from this layer to connect to this layer. These are called feedback connection, they are not allowed. So, that is why this is known as feed forward network. So, today we will derive a 2-layered feed forward neural network with sigmoid activation function. You can very easily see this is one layer, this is only hidden layer, and this is the only output layer. Of course, output layer is always only one. What we will do, we have a certain convention that we will put while deriving a back propagation learning algorithm for this. The same simple principle, given training data, we allow the input to pass through the network, compute the error here, use the gradient descent rule, and the back propagated error are used to modify the weights here, that is between output layer and hidden layer. And again another form of back propagated error here has to be used for modification of the weights between input layer and hidden layer. So, this is the again the convention that we will use is I is the index for a typical neuron in the output layer, this you can see here. I is the index for the neurons that are used in this output layer, J is the index for the neurons used in the hidden layer, and K is the index for the input patterns, and the weights for a typical weight that is between hidden layer and output layer is denoted or represented by W with suffix ij. Similarly, because I is here and J refers to this particular unit layer, and here the weight, a typical weight between input layer and output layer is represented by Wjk, where J refers to the index for hidden layer and K refers to the K is the index for input layer. So, this is what we have said here, I, J, K, 3 different indexes for 3 different layers, input, hidden and output. And this is the weight, typical weight representation between hidden layer and output layer, and this is a typical weight representation for the weights between input layer and output layer. Now, derivation of the back propagation algorithm. First, what we do, as I said, in the network, you allow the input to pass through the network and compute the response y 1, y 2, y n. So, to compute y 1, y 2, y n, we assume that these hidden units had output also v 1, v 2, v 3, and these output are first computed, the output of the hidden units are first computed, and using the output of the hidden unit, the output of the output layer are computed. Just for the clarity, again I say all these neurons are sigmoidally activated, means they use sigmoid activation function. So, you can see that Vj is 1 upon 1 plus e to the power minus Sj, where Sj equal to the total input reaching the jth neuron of hidden layer. Similarly, output of the ith neuron in the output layer is 1 upon 1 plus e to the power minus Si,
where Si equal to sigma Wij Vj. So, Si is the total input reaching the ith neuron in the output layer. So, here we are computing the cost function for instantaneous update, which is this value equal to half yid minus yi square. So, the gradient descent rule is same for the weight update rule. For weights between hidden layer and output layer will have this particular step, that is the principle of gradient descent. Wij t plus 1 is Wij t minus eta del E by del Wij. Weight update rule for weights between input layer and hidden layer is Wjk t plus 1 equal to Wjk t minus eta del E by del Wjk. So, how do you find now del E by del Wij and del E by del Wjk? So, this is what you have to find out. So, here we sort this diagram, again I drew on the blackboard for the clarity, because I would like to derive this whole thing in the blackboard. You have input x 1, x 2 up to x p, you have output y 1 to y n. So, n different computational unit, and you have hidden layer with m hidden neurons whose outputs are V 1, V 2, V m, and as I said Wij is a typical weight connecting ith neuron in output layer with jth neuron in the hidden layer, and similarly Wjk is a typical weight between hidden layer and input layer. So, what we will do in the first phase, we will allow this input to pass through the network and we compute what is y 1. So, let us compute that. So, what we are doing? We are computing the output of a hidden neuron Vj. Vj is the output of the jth neuron of the hidden layer, is 1 upon 1 plus e to the power minus Hj, where Hj is the total input reaching the jth neuron, and Hj is Wjk xk. So, if you go back, you see here Vj. So, for example, I want to compute what is V 1, what I do? I compute what is H 1, and H 1 is W 1 k into x k sigma. So, that is W 1 1 into x 1 plus W 1 2 into x 2, W 1 so on plus W 1 p into x p. So, this way we compute what is V 1, V 2 and V m. And now, we compute what is, after we computed what is V 1, V 2, V m, we will now compute what is y 1 up to y n, y 1 up to y n. So, this computation is y I is 1 upon 1 plus e to the power s I, where s I is sigma W I j into V j. So, this you can also verify in the previous one. For example, I want to compute what is y 1, I will multiply, first I will compute what is s 1, and s 1 is, you can say s 1 is W 1 1 V 1, W 1 2 V 2 and so on, plus W 1 and the last one is m into V m. Once you compute what is S 1, the next stage is y 1. Y 1 is 1 upon 1 plus e to the power minus S 1. This is a sigmoidal activation function. So, we are done with how to compute y 1 to y n given x 1, x 2, x p using forward propagation. Now, we go to computing the error at the output. So, I am given actually what is y 1 d, y 2 d, y 3 d and y n d. This is given. I compute what is y 1, y 2, y 3 and y n. This is computed. So, network computes y 1, y 2, y 3, y n given y 1 d, y 2 d, y 3 d, y n d. So, I compute the cost function E. Instantaneous cost function is half y d I minus y I square sigma over I. So, I subtract from y desired to y, square it and add for all the output units in the output layer. So, that is how I compute the cost function. This is called instantaneous cost function. And this instantaneous cost function is computed for a specific pattern. We are not for a given pattern, I compute this cost function. Now, I go to the next test. Once I compute what is E, I have to compute the as I showed you for the weight, a typical weight between hidden layer and output layer, Wij, the weight whatever is was previously in a previous iteration, whatever is Wij, that has to be updated by adding a gradient term. So, this is the weight update for weights between hidden layer and output layer. And all that you have to do is simple derivative principle, how to differentiate given y and you know the function structure. So, you simply differentiate. So, all that we have to do is that del E upon del Wij. If I can compute, I just have to put it there in this equation. So, this is equation 1. So, to put that I differentiate del by del Wij, and here I have half sigma I y d I minus y I whole square. So, you can say that only the ith, the error contribution due to ith neuron is a function of Wij. Hopefully, you are very clear. You say that is if I am considering this particular unit, this is my typical weight which is W11 and I want to update W11, then you should be very clear that this only the error computed here at Y1 is a function of W11. You can very well see Yn is not a function of W11. So, once you are very clear about that, I can write this one as del by del Wij half y d I minus y whole square. Other terms are not relevant. We go again. So, we continue. So, del E by del Wij we found out to be del by del Wij half y d I minus y square. So, that is obviously you can check it y I d minus y I into here minus del y by del w I j. Hopefully, you are now clear with this expression. This is I can say equation number 2. Now, from equation number 2 we have to find out what is del y I by del w I j. What is y I? Y I is 1 upon 1 plus e to the power minus s I. So, del y I by del w I j has to be written like this, del y I del s I into del s I by del w I j. We go to the next step. If y I is 1 upon 1 plus e to the power minus s I, and for we have already discussed this kind of activation function, if I differentiate s I, then I find the answer is y I 1 minus y I. This we have already said. So, the rest is left with del s I by del w I j. So, to find out del s I by del w I j, I must write down del by del w I j, and s I is sigma w I j into V j. So, this is simply V j, okay, because this is simply summation of terms. So, with respect to w I j only V j comes out. If you want to differentiate with respect to w I j, V j comes out. So, we are now finally reached this solution, that is del E by del w I j is minus y d I minus y I into del y I upon del w I j, which was the equation number 2. So, that reduces to minus y d I minus y I into here y I 1 minus y I into V j. So, this is the final expression. So, this term comes from del y I upon del s I, and this is from this term comes from del s I upon del w I j. So, what was our earlier update equation? W t plus 1 equal to w I j t plus this was actually minus, I am making plus because I am getting here minus eta del E upon del w I j. So, that was minus. So, here the term is minus. So, this is becomes plus eta y I d minus y I into y I 1 minus y I into V j. So, this is your final equation for the weight update law for weights between hidden layer and output layer. So, finally, I write down the weight update equation for the weights between hidden layer and output layer is eta delta I V j, where delta I is y 1 minus y So, this should not be surprising to you, because for single layer neural network also, for nonlinear neural network we found delta to be of this form and the input is V j. Okay. So, I will not now derive the next update equation that is required for the weights between hidden layer and input layer, which is Wjkt plus 1, which is also has a similar formula, that is Wjkt. You can just take little pain to find out this is delta j xk. You see that it has a very nice formula where delta j is Vj 1 minus Vj sigma delta I W I j over I. So, I give this as an exercise for you to derive this weight update equation. This is an exercise. Okay. So, all right, we are done with the derivation of the back propagation learning algorithm. I just explained in the figure that we pass the information from here to here. We have a general weight update algorithm for this weights here, and another general weight update algorithm for the layers here. So, that is the summary of the weight update algorithm. So, what you learned today, the gradient descent algorithm, the derivation of this algorithm for multi-layered neural network. We will apply that derivation for learning the XOR map, which we could not solve using single layer feed forward network using nonlinear activation function. So, as usual, this is our cost function and this is our model of a XOR network. We have two input x1 and x2, these are our weights, and we have put two bias units. This is the bias weights, that is 1, I have a fixed input 1 and the weight is T1, here is T2. You can also say this is if you consider this 1 to be here and another input, external input, then you can also easily say this is W13 and this is W23. So, this is W13 has been represented by T1 here and W23 is represented by T2 here, and these weights, just for clarity, we have kept W10 and W20, and the bias weight has been has kept as T0, that is the input is 1 and the weight is T0 and the output is Y. So, now you update the weight, this is a T0, W20 and W10 using the weight update, that the algorithm for Wij, and T2, T1, W11, W12, W22, W22 you update using the weight update algorithm for Wjk. So, if you do that, you start with all these weights, you initialize between minus 0.1 to 0.1 and eta has been taken as 0.75, and let us take the number of iterations as 50,000. What is iteration? I take all these patterns sequentially. So, I have 4 patterns and 50,000 means I have taken these 4 patterns again and again until 50,000 iterations are over. So, for that you see the weight vector that is obtained for hidden layer, between the hidden layer and between hidden layer and input layer is this one, and this is the output layer, the weight between output layer and hidden layer. These are the bias weights T1, T2. This is for, again you can say this is for hidden layer and input layer, and this is for output layer, the bias. And this is if you After training, if you give this input, this is x1, this is x2, this is my desired output, and the actual output is very close to desired output. You can say it is almost exact. This is your error plot. You can easily see the, although we have taken 50,000, but actually within 5,000 the training is over. So, there is no, it is not necessary to actually go up to this, and in subsequent lecture we will say why we should not train further after training is over, because after 55,000 literally there is no training, and this causes the problem of over generalization, and that will be discussed in the next class. Now, here is assignment for you. The first one, please note down this linear dynamical system where the coefficients are minus 0.75, this is a second order system, minus 0.65 and here 1.25. You allow that this is to be W1, W2 and W3. Assume W1, W2, W3 is very small random number. Use the training data using this model where U is a random number uniformly generated between 0 to 1, and apply this input data, use this input data to train the neural network, linear neural network, and you should finally get the answer. W1 should be minus 0.75, W2 should be minus 0.65 and W3 should be 1.25. This answer you should get. The second one little may be difficult for you. This you have to use a multi-layered neural network, feed-forward network. I suggest you use around 10 hidden neurons. Obviously, you have one output. So, one output, the output layer has only one neuron, input also has only one UK. So, take only one input in the input layer, one neuron in the input layer, sorry, input layer has only one input, you can include one bias input. You generate the data for this using this actual model, taking UK again randomly generated number from 0 to 1, and then normalize these values YK and UK between 0 to 1, because your neural network has an activation function whose output is between 0 to 1. So, you have to normalize output also between 0 to 1, and after that you train. After training, just like you could correlate in the case of linear dynamical system, you cannot correlate because your neural network becomes a black box. We will discuss this more, but what you can verify, you give new data to this neural network, to this actual model, new input data, and for that new input data find out what is the output. Giving this new input data to your trained neural network, you should be able to get what is the desired output. Okay. So, goodbye, we meet in the again next class.